Hi everyone, my next topic is sound, the auditory system, and pitch. Now if you're thinking, I'm so glad all that vision stuff is over, all that hard stuff, it's going to be pretty easy stuff from here on to the end. No, do not underestimate auditory perception. Some things are pretty complex, and I'm going to be going over it, doing my best to explain it. Again, I don't want you to underestimate this, but I'll help you through it. Let's take a look at the learning outcomes for this section. We need to start off with a bit of physics. Yes, just a little bit of physics, how we can describe sound physically and perceptually. We'll take a look at timbre of a sound. We'll take a look at loudness and something called the equal loudness curve, and I will explain something in the textbook that is a bit confusing. Next, we'll take a look at some structures of the ears, the functions of those structures, what they do, the outer, middle, and inner ears. We'll zoom into the receptors for audition and take a look at the transduction process. We will follow the path that the information takes from the ears to the brain. I'll talk a little bit about pitch perception. It's actually going to be a couple of families of theories. So if this looks like a big long list, okay, don't worry about it. I'll show you how they all fit together. And they do all fit together. And for the last one, I want to look at tinnitus and also noise and how that affects our hearing and how we can prevent hearing loss. So a bit of a public service message for you. Yes, it's going to be on the exam. Okay. We're going to start off with a definition of sound, which might seem a little bit silly. Well, everybody knows what sound is. Still, we need to have a definition for that. This is the scientific approach. We have to be precise, and it may actually help us in many ways. So the definition for sound we're going to work with is pressure waves in the air produced by a vibrating object detected by the auditory system. Now, this last part is really important. This will help us potentially to solve age-old riddles. Like, for example, if a tree falls in the forest and there is no one there, does it make a sound? Well, it does make pressure waves, but if there is no person or animal there with an auditory system, technically it does not make a sound. The distal stimulus is a vibrating object, or at the very least, some object that is delivering kinetic energy to air molecules. The proximal stimulus is that kinetic energy. So once again, our sensory systems are all about detecting energy or chemicals. And in this case, again, energy. Now we do need to understand a little bit of the physics of sound, and this will help us to understand how we perceive sound. Now, sound comes in waves, and, well, not to put too fine a point on it, here is a wave. Now, there are some important characteristics of a wave that I've tried to highlight. I'm going to start with, I think, the most complex one, and that is phase. Never really come across a wonderful definition for it. This is kind of the best. The point along the wave. So where we are on the wave. I know that doesn't make a lot of sense. We start off with a phase of 0. The wave is just starting out. It reaches a peak at 90. It starts to go down until it reaches a minimum here at 270 degrees, and by 360 degrees, it has completed a cycle. So it is measured in degrees. I have to point out there is no direct perceptual counterpart to phase. And you might think I've just wasted your time, but there's something key in the way that I just said that. That's going to be important. Okay, there are a couple of other important components here, including the amplitude. So going from the peak to the trough, basically, and then there's also the cycle. So starting at 0 and then going back to where it started. I want to focus on amplitude for a second. It is the displacement of a wave from peak to trough. The range that we are able to detect and process is actually incredibly large. Our threshold is about 0.0002 dynes per square centimeter. That is a measure of energy over a two-dimensional area. The maximum of hearing is about 200 dynes per square centimeter. And that's where sound stops being sound and basically just turns into pain. That means that there's a difference from the threshold to the maximum of about 1,000,000 times. I know that's kind of difficult to see because of the decimal points and everything, but this is a huge, huge range, and that kind of makes it awkward to work with. So instead of just working with this, for large ranges, we like to take a logarithmic scale. It's kind of easier to work with in one way. The numbers are smaller, although it is a little bit more cumbersome, on the other hand, if you're not used to working with logarithms. To make this a little bit easier, there is a familiar scale, and that is the decibel scale. Now, this is actually based on the Bell scale, named after Alexander Graham Bell, and that's why the B here is capitalized. I don't know why decibels doesn't have 2 L's, though. A decibel is literally a tenth of a bell. So the Bell scale was still a bit too big, so to get some nice round numbers to work with, we take a tenth of it. And here's the way we calculate a decibel. It is 20 times the log of a bunch of alphabet soup. Okay, let me explain the alphabet soup. P here is the sound pressure level of the sound that we are interested in, and P sub 0 is a threshold SPL, or sound pressure level. It's kind of a reference at 20 micropascals of pressure. Now, this particular sound is just barely detectable 50% of the time, hence the use of the technical term threshold. So any sound that we want to calculate the decibels for, that's being calculated with respect to this P sub 0, which is this particular sound pressure level. Here are some example decibels. We can start off right at the top, about 180 decibels. That's you standing far too close to the space shuttle, and you might be concerned about your hearing if you're standing that close, but that's nothing to be concerned about, because the space shuttle is about to fry you to a crisp, so losing your hearing is really the least of your worries. Amplified rock band at about 150, a jet airplane below that. Jet airplane is not the name of a rock band, although that would be a cool name. Jet airplane is actually below a rock band. Yikes. Okay, loud thunder at 130. Now, this image I have, for some reason, it's been colored a nice friendly shade of blue above 120, but this actually means you're about to suffer permanent, irreversible hearing damage. The alarmingly red region here means you are also in the potential range for suffering some hearing loss. I'll get to that in a second. So a typical subway or a train is about 110 decibels. Heavy traffic at about 80. And this brings us to the friendly shade of green down here, which means you can be exposed to these sounds for a really long time, and you don't really have to worry about any hearing damage or hearing loss. So there's heavy traffic, and then an average automobile, a normal conversation, a quiet automobile, a quiet office. A whisper at 5 feet is 20 decibels. Tree leaves blowing in a slight breeze is 10 decibels. And your threshold of hearing is 0 decibels. Wait a minute, what? Your threshold of hearing is 0 decibels? You can hear 0 decibels about 50% of the time? That doesn't make sense. Oh, yes, it does. Remember, my definition of decibels was with respect to our threshold? So if you can pick up a sound of 0 decibels, that doesn't mean there's nothing there. That actually means it is, by definition, a threshold sound. So don't let that 0 number throw you off. So I was mentioning hearing loss a little bit. So it isn't absolute. It isn't all or none. It isn't what is a safe level. Okay, so there is a bit of dispute about this a little bit, but basically you can have indefinite exposure to a sound below about 56 decibels. It is not going to cause any kind of permanent, irreversible hearing loss. Between 56 and 80 decibels, you would need over 8 hours of exposure. That's a long time to be exposed to things that are pretty darn loud. Between 80 and 100 decibels, you can be exposed between 2 to 16 hours. And then I've colored things red for the remainder. If you're exposed to something about 175 decibels, you could stand that for maybe half a second before suffering some permanent irreversible hearing loss. Just something to keep in mind. Okay, so I was going over the parts of the wave. Let me turn now to frequency. So this is the number of sound wave cycles per second. And of course, you can't see frequency anywhere here on this diagram because it has to take into account the cycles per second. That's how we calculate it. The units are hertz, named in honor of Heinrich Hertz. So it is the number of cycles completed in a unit of time, which, again, that would be seconds. So not too hard to calculate. Are you going to make us calculate this on an exam? I don't know. Maybe you should know what hertz are and how they're calculated. Okay, so let me switch from some of this physics stuff to some perceptual aspects of sound. I want to bring in loudness. So loudness, once again, is something that corresponds to a physical unit. So loudness is our experience of the intensity of a sound. I'm not going to be using the word volume because volume is not a scientific term for anything. It is not a property of physics. It's not a perceptual aspect. I don't know what it is. Really, the term that we should be using is loudness and not volume. So loudness, that perceptual aspect, is associated with amplitude and sound pressure. I'm not saying it's the same thing as. That would be incorrect. Okay, but loudness is the result of amplitude and sound pressure and some other things as well. Now we can actually measure loudness by comparing a given sound to a standard sound. Yeah, but what sound are we going to pick to be a standard sound? Okay, that's already been done. So it was settled that 1000 hertz is a pretty good standard sound. It's right in the middle of our range of hearing. Even if you have some hearing loss, you probably still have some residual hearing at about 1000 hertz. It's also a nice round number, so you generate a 1000 hertz pure tone. So if you were to look at it, it would look like a sine wave at 40 decibels. That particular sound is called 1 sone of loudness. Now this is pretty interesting because now we have an actual unit of perceptual experience. We haven't really had that before. Color, that's not a unit. Again, color is the result of the wavelength of light, but again, we haven't really had a unit of perceptual experience. So a sone definitely is that. So if you generate a sound, it might be, it might sound twice as loud as this 1000 hertz tone at 40 decibels. So that sound would then be 2 sones of loudness. So it's pretty cool that we have units now for perceptual experience. There is kind of a rule of thumb. To double the loudness, you would increase the decibels by approximately 10 decibels. It's kind of rough. It's not perfect, but it's pretty close. So that means, and this is where logarithms are kind of tricky and difficult to deal with, that means a 60 decibel sound is actually twice as loud as a 50 decibel sound. I know that's kind of unintuitive. It's kind of difficult to kind of wrap your arms around, but that's something to really, really keep in mind. So logarithms can be a bit tricky. Okay, so loudness is one perceptual aspect, as is pitch. Now, of course, I'm going to be coming back to pitch at the end of this lecture. Pitch is a quality of a sound ranging from low to high. And this is what underlies our experience of music. We can compare different sounds or notes together and place them on a musical scale. Now, usually my approach has been to give you the simplified version first, hopefully not the oversimplified version, and then to add some complexity back. So I'll do that here. Pitch is most closely associated with frequency, which ranges from 20 to 20,000 cycles per second. That is kind of the best case of the range of human hearing. We will be coming back to that as well a bit later on. But again, this is a simplification. There are other factors that influence pitch. For example, intensity. So, getting more specific, a given high-frequency sound seems to be higher pitched as you jack up the intensity or the loudness. Same is true if you take a low frequency sound, its pitch seems to get lower as you jack up the intensity or loudness. So this shows an interaction between intensity and pitch. I also have to point out, if the sound is not on long enough, if it's on very briefly, like less than about 10 milliseconds, the sound wave is there, okay? The actual physical stimulus is present, but perceptually, we will experience that sound not as a pure sine wave having a specific pitch, but rather it sounds like noise. It sounds kind of like a click. So it looks like we have to be experiencing a sound for a certain minimum duration in order to be able to extract the pitch information out of that. Okay, so this is talking about a specific pitch or frequency. We can get a little bit more complex. We can look at the relationships among frequencies, comparing two different frequencies to each other. And no, not just random ones. I am actually talking about music. So music is partially defined by the scale. So this is kind of the toolbox you have of the notes that you can take and put them together in various different ways. They might be played simultaneously or in succession. So we might have harmony, we might have melody, for example. I'll get to music in a bit more detail. Again, coming up a little bit later. Is everything coming up later? Yeah, it is. Okay, I'm trying to give out the information not in a fire hose, but just to kind of trickle it out. Okay. So, the so-called chromatic scale of musical notes, sometimes called the well-tempered scale, this has nothing to do with temper, like getting angry. No, it's all about the division of frequencies into the notes of a musical scale. So, I will go with the most common Western scale. So, one note is said to be an octave above another when its frequency is double that. Okay, so it's all based on some pretty nice, I'll call them round numbers. So the octave is based on a doubling of frequency, interestingly. The octave is then divided into 12 intervals or semitones for you musically inclined, and these are equally spaced not linearly, but logarithmically. Yeah, there's those logarithms again. Okay, so this is a representation of a piano keyboard, and we have the different notes, so A3, B3, C4, and so on. And we also have the black keys as well, and then the corresponding frequencies. Now, just eyeballing it, you can't tell by looking at these numbers that these are equally spaced logarithmically. You'd probably have to graph it in order to be able to see it. But we can compare A3 here to A4, that is this note here at 220 hertz, to the octave above, which is 440, which is, yes, a doubling of the frequency. Now, why would the musical scale be divided this way? It seems, I don't know, unnecessarily complex. Did someone actually sit down and decide, I'm going to space things out equally logarithmically? No. No, from the evidence that we have, it didn't happen that way. Rather, the tones were decided to match the harmonic ratios found in human vocalization. It has been found in English vowel sounds. It has also been found in other languages, different Chinese dialects as well. So, if anything, it appears that music has taken after language. Now, not everybody agrees with that. There's actually quite a large debate going on about that, so I will just leave that out there. Now, this is only one way of taking the spectrum of frequencies and dividing them and placing them into different notes. It's not necessarily the right way. It might be the way that a lot of us have had most of our experience with music. But there are other scales that use different ratios. They're called microtonal or microtuned. My synthesizer, for example, that I have can actually be programmed with some of these different scales. Now, they might not be super common. You might not have heard these before. So let me play you a little brief piece of music from some classical Arabic music. Now, we can take a single musical note and analyze it. Analyze it in terms of its components, using something called Fourier analysis, which again, we can take a complex waveform like the one on the left and subdivide it into its pure sine wave components. Now here, there's one special component. It's called the fundamental, and this is the lowest frequency in the Fourier spectrum. So this complex waveform has been divided into 3 separate waveforms. They all have roughly equal amplitude or height, but they definitely have different frequency. So the one on the top here has the lowest frequency. This one would be the fundamental frequency. And then all the others, well, they're all called harmonics. And typically, when it comes to music, the harmonics are multiples of that fundamental, multiples in a mathematical sense. So it is these harmonics, plural, how many of them and which particular ones and their amplitudes that combine together to create the nature or the timbre of a given sound. Which, let me get to timbre. So it is pronounced timbre, or I suppose timbre. So French, it's not timber, okay? Don't call it timber. Timber is what you say when you chop down a tree. Timbre is one of those things that it's pretty hard to define. It is the character of the sound. It is the nature of the sound. It's what a sound sounds like. That's a terrible definition. Sorry. It's one of those things that, well, you know it when you experience it. It's what makes a violin sound different from a piano, makes it sound different from a human voice, for example. It's those different harmonics that all contribute. Again, it is all those different frequency components, the fundamental plus the different harmonics. So these are 3 different notes. First one is a clarinet, next is a trumpet, and this one is a piano. I'm not sure if they're playing the same note, but they definitely have different frequency components. I want to play you a few sonic examples of different sounds. So I'll show you what they look like, and then I will play them for you. So first we have a pure sine wave tone. It's been described as kind of a whistling. What you see here is what it would look like, okay, if you could see it. And then next, I've actually got the Fourier spectrum. So a sine wave has only one sine wave component. That kind of makes sense. Let's try a square wave. Okay, clearly looks way different. Fourier spectrum also looks different. What does it sound like? That's pretty annoying. Okay, I don't really like that one. Let's try a sawtooth wave. Again, a very different looking spectrum. And that one sounds, I'm going to turn the sound down a little bit. That one sounds like this. Do you see why I turned it down? Yeah, pretty annoying there. And finally, a triangle wave, which you might think that's the same as a sawtooth. Well, give it a listen. No, it's actually very similar to the sine wave. Okay, but those are some basic kind of building blocks. These have been described as sounds that do not occur in nature. Yeah, you don't really find them. You don't really find a bird making the sound of a sawtooth wave. So let's go to some synthesized instruments, like an oboe. So this is a 400 hertz oboe tone. It's not an actual oboe, it is synthesized. It sounds like this. That's a pretty crummy synthesized version. Okay, and here's a clarinet. So again, it looks very different and it sounds pretty different as well. All right, let's go to some basics of audition, including auditory threshold. A lot of this work goes back to 1933. I can't give you the number for auditory threshold. It's more complex than that. It's not a single number. Auditory threshold is actually a set of numbers. It's a collection of numbers. There's a different number for every different frequency. Okay, so it's not one single threshold and boom, we're done. No, we have to take it frequency by frequency. Makes it a lot more complex. This collection of thresholds, if you like, is called the audibility curve. So I'm going to be showing you diagrams that look like this quite a bit. On the x-axis, we have frequency. You can see going up by orders of magnitude, up to about 10,000, up to maybe 20,000, and then the decibels along the y-axis here. Along the bottom edge of this blue blob, we have basically your absolute threshold. So every different frequency has a different threshold level. And you have your lowest threshold at around about here, about 3,000 or so hertz. So it's clearly not a straight line going straight across. We also have an upper limit here, and this is where sound basically stops being sound and turns into pain. So there's kind of another threshold here. This is, I guess you'd call it your pain threshold. So this blue blob area that I mentioned is called the auditory response area, and it includes the dynamic range that you are sensitive to. So the dynamic range is kind of the vertical space from one threshold to the other. At very low frequencies, we have a very small dynamic range, but about 3,000 to 5,000 hertz, we have a very large dynamic range. So even for dynamic range, I can't give you a single number. I could give you the maximum dynamic range. If you're shopping for high-end audio equipment, like some really nice headphones or some really seriously good speakers, they will have that information for you, the maximum dynamic range. Beyond just threshold itself, we can get to, yes, slightly more complex concepts, like the equal loudness curve. Now this one is a bit more complex. It is a graph, once again, of decibel levels of different frequencies, okay? So we're manipulating both of those things, decibel levels and frequencies, but the goal is to manipulate those two quantities to make the sound a consistent, equal loudness. I'll talk about how to get it, then we'll take a look at the results. How you get it? Well, you go to that standard tone again, 1,000 hertz at a certain decibel level, like maybe 40, but it doesn't always have to be at 40. You'll then present other frequencies to match the loudness of that standard. So again, what you might do, take a 1,000 hertz tone, let's say we start at 40 decibels, and then you take other frequencies and adjust them individually until they seem just as loud as a 1,000 hertz tone at 40 decibels. And what you're going to find is that all these different frequencies will have to be adjusted, and they won't all land at 40 decibels. Okay, let me show you the graph. And this is the problematic graph. This is the graph that students have found confusing for many years. Unfortunately, this is the one that's still in the textbook. It hasn't been changed. Now, it does show you a couple of things that we've seen already. It shows you the audibility curve. Here it's colored in green. Pretty similar to the one that I showed you before. And up here we have basically your pain threshold. Here it's called your threshold of feeling. But it also shows another couple of equal loudness curves. Now, what I think is confusing are these two arrows. This makes it seem that this is saying these two curves are equal in loudness to each other. They are not. These are two different equal loudness curves. Now, what is equal is, as we travel along this curve, every single point is as loud as every other point. Now, as we travel along this curve, we are changing frequency as we go left to right. We're also changing the decibels a little bit as we go up and down. But what is not changing is the loudness of the sound that you hear. It will be changing in its pitch because we are changing the frequency. The sound pressure level is changing, but again, what does not change is the loudness. Now, this top curve is called the 80 equal loudness curve because it is defined with respect to a 1,000 hertz tone at 80 decibels, and that's this spot right here. This one is the 40 decibel equal loudness curve because it is defined with respect to the 40 decibel 1000 hertz tone. Again, every point along this curve is equal in loudness to every other point along this curve. But the 40 and the 80 are two different equal loudness curves. These two curves are not equal in loudness to each other. The 80 curve is way louder than the 40 curve. If you do the math, the 80 curve is about 16 times louder than the 40 curve. So clearly, they are not equal in loudness to each other. That's an important takeaway. But I know this is kind of weird to grab onto, so I do have some auditory examples for you to listen to. I want to compare and contrast equal loudness and equal amplitude. So first, let's listen to an equal loudness curve. Now, one thing that's very distracting I got to tell you about is it changes in pitch, okay? So it's going to start off low pitch, and then it's going to go high. Try to ignore the pitch and just focus on how loud the sound is. What you're going to get first is an equal loudness curve. Check this out. Okay, that wasn't really loud. I'm going to crank up the volume on my end, and we're going to try it again. Now I realize, again, the pitch is very distracting, but that sound should not have changed in its subjective loudness. Now let's contrast that with a sound that has equal amplitude. Again, it's going to start off with a very low pitch and go to a higher pitch, but I want you to focus now on the loudness. Does it have an equal loudness? Now what you should get, especially towards the end, is it should seem to get louder. Well, why is that if it's equal amplitude? Again, amplitude and loudness are not the same thing. Amplitude is a physical dimension. Loudness is a psychological dimension. If you didn't hear it the way I described, that it should be, these are the highest quality sounds I can come by, maybe you should upgrade your audio equipment. Okay, coming back to auditory threshold. Auditory threshold is affected by other factors. This is kind of a theme we're going to be seeing over and over and over again. Auditory threshold is affected by auditory adaptation. This should come as no surprise. If the same sound is being presented without changing, without going away, our sensitivity to it is going to decrease over time. That can affect our threshold. We can also get auditory fatigue, which is a bit more serious. Auditory adaptation can happen to a sound really no matter what the intensity is. Auditory fatigue specifically applies to high-intensity sounds, and it is a temporary hearing loss. We can also differentiate these two another way. Adaptation affects the one specific frequency that has been presented, but fatigue has kind of a spillover effect. Fatigue will affect the frequency that was presented, but will also affect higher frequencies. So from 1.0 to 1.5 times the frequency that you were presented with during the adapting phase. So for example, if you're exposed to a 1000 hertz tone, auditory fatigue would be you are seriously decreased in your sensitivity from the range 1000 hertz to 1500 hertz. So that's 1 times 1000 up to 1.5 times 1000. If it were just adaptation, you would only be affected at this one single frequency. I'm going to stop there.